Go figure.
All right, so we're here going deep, going into the audio the Vista audio stack. We have Larry Osterman and a special guest today.
And Elliot Omiya, who is...
I'm an architect and one of the lead developers on the audio stack in Vista. So we're here to talk about audio and the changes in Vista and how you program the audio in Windows.
Fantastic.
So
Very
Elliot's also responsible for the plumbing, the engine. He does all of the stuff that actually makes the audio bits show up and make sure that they sound really good and stuff like that. I work on high-level plumbing, but Elliot's like the core.
The core.
Low level. He owns all the hardcore low-level stuff.
Now, of course, the low level is now up in user mode, though, right?
Right. So that's one of the big changes in Vista now is the low level used to be kernel mode drivers, and now the low level is a user mode stack. And of course, there's still audio drivers, but they sit directly on top of the hardware and plug into a mini port driver model called port class, which we'll talk about on the whiteboard in a little bit. But that's the last part of drivers that we have. That's the last part of kernel mode programming we have. Everything else is in user mode.
And now, can you let me talk about briefly, like what are some of the advantages of besides crashing in the kernel and the danger there?
Well, there's two main reasons that we did that. The number one reason is reliability, because if a plugin component or some Microsoft code makes a mistake, we take down the audio stack. We don't take Windows. So increases reliability because it reduces blue screens of death. The second reason is, truthfully, there's a lot more people who are capable of programming in user mode than kernel mode, and so it increases the pool of talent we have available to work on the audio system in Vista. So those are the main things. And it also has some implications for the industry in the second part, because in the general population, there's even fewer kernel mode experts and capable developers in the world. And so if we can make audio programming more approachable by doing it in user mode, then we've increased the pool of people who can make multimedia and audio-oriented applications on Windows.
In the optimal cases, and we're working very hard to make sure that this is more and more cases, but in the optimal case, the act of rendering an audio stream to the driver, to a sound solution, to an audio adapter, involves no driver code at all. In the best case we've got, you set things up at the beginning with the driver, and then from then on, all of the audio processing is done just by simply talking directly, essentially to the DMA buffers on the audio adapter itself. So it's the audio engine talking directly to the hardware, and you never see a driver doesn't enter into the picture, and so if there's no driver in the picture, then there are fewer instructions of code that can take out the operating system. And that's really important. So, we don't want to have anything there that's going to take the system out. So
fantastic. Now, you guys basically completely rewrote the audio stack for Vista. Is that fair to say?
So there are a number of kernel mode components that no longer exist in Vista. One is called sysaudio, which was a filter graph stack that we had, and a component that some people have heard of called the K-Mixer, and both of those components are gone, as well as every filter driver that ever plugged into sysaudio. And one of the examples of that is the redbook.sys driver, which implemented the analog ioctals for Redbook CD play. That was implemented as a filter driver, and all of those plugins are now gone.
So you can actually see this if you look at the Vista Beta 1 stack and you play an analog CD with MPlay32, the old CD player. If you use that, you'll discover that it doesn't totally work. And it does work in certain circumstances, and if you have the right hardware set up, it works. But for some set of people, it doesn't work, and that's because we ripped out those kernel mode solutions that were built on top of the legacy implementation. For Vista Beta 2, we have a different solution that allows every app we've found that's playing audio to continue to stream audio through their CD and without going into the kernel mode. We basically moved that CD playback infrastructure out of the kernel and up into user mode for that as well.
So is it fair to say that with today's processing power, that the performance gains you can get in kernel mode aren't necessarily as important as they used to be. What I mean by that is you can move, so as you move the audio stack up into user mode, there has to be some sort of performance implications of doing that.
Yeah, I think there are a lot of performance implications, and the first thing you might think is, oh, what kind of hit did you take when you went from kernel mode to user mode? And it's sort of a myth that kernel mode processing is more efficient than user mode processing. What really gets you hung up is kernel user mode transitions, which can be very, very expensive. And the way we've built the architecture of the Vista audio system, we avoid that in many ways. And when we have to make the inevitable transition from user mode to kernel mode, we've done that in a very interesting way that doesn't require any instructions. This is the thing that Larry was referring to before. So when we get on the whiteboard, we can talk about what WaveRT means in the Universal Audio Architecture Initiative. So we've been very, very happy with the performance and the glitch resiliency of the Vista audio stack. And one of the big changes that we made was changing from an integer 16 to a float 32 pipeline, which I don't know if we have time today to go into the sonic advantages of that, but basically a lot of digital signal processing algorithms are much less amenable to distortion and artifacts when you have a bigger number to play with. A lot of today's music content is authored so what we call hot, that if you apply DSP to it, like equalization or mixing, you often will overflow a 16-bit integer and create all sorts of bad sounding artifacts. So we have used some of the advantages, the performance wins that we got by the redesign of the audio stack, and spent a little bit of it on better audio fidelity by going to a float 32 pipeline.
Fantastic. Well, it'll be fun to talk a little bit more about that for sure.
Right.
Well, let's get on. So what does this look like?
Okay.
Let's draw it out.
Let's start with the high-level application stuff, the plumbing, the areas that I work in day to day. The very top of the audio stack in Vista, well, the audio stack in Windows, you have WinMM. WinMM is actually one of the oldest components of Windows, period. It was introduced in Win 3.1, and this is the host for the multimedia extension APIs. So the Wave APIs, Mixer APIs, MIDI, and everyone's favorite PlaySound are all hosted inside winmm.dll. The next large piece of infrastructure is dsound, and layered on top of direct sound is direct show. For Vista, we have another high-level infrastructure called Media Foundation, and Media Foundation is basically it's a new paradigm for rendering audio samples into the system, and it has a whole series of different advantages in terms of the way that it's architected. If you use direct sound, if you use it, it has some limitations and it can be very resource intensive. Media Foundation is intended to solve a lot of those issues. It's also designed with glitch resiliency in mind at the start, so you have the ability to more tightly control and better implement glitch resilient audio playback. So a large portion of the audio playback that's used for, say, Windows Media Player, for instance, in Vista, will actually be going through this new Media Foundation infrastructure. Living under sheet underneath winmm.dll is another driver called wdml.drv. This is actually where the actual implementation of all of those APIs mentioned, except for PlaySound, lives. So wdml.drv is actually where the Mixer, Wave, and MIDI implementations live. Underneath all of this,
and I might add, there used to be a wdm.sys.
Yes.
And that's one of the kernel mode components that no longer exists. So it's technically not a DIRV anymore.
Yes.
It's really just a DLL.
A DRV was what they called back in Windows 3.1, was it? Windows 98, somewhere in there. When they first put out the Windows driver model, WDMOD, for audio, they had paired components, the DRV and a sys, and the idea was that the DRV forwarded to the sys, which actually did the work. We don't do that anymore, but we kept the name for legacy reasons because, well, frankly, because there's a whole bunch of stuff in the registry that references it, and it was just easier to simply call it WDMOD.DRV, even though it was technically no longer a DRV in the sort of Windows driver model sense.
Okay.
So living underneath all of this are a series of essentially 3 API families. The first is called MMDev. The Multimedia Device API. And the Multimedia Device API is basically an API that allows you to enumerate audio endpoints. And an audio endpoint is a new concept that we've introduced for Vista. When users think about their audio solution, they don't usually think about, I don't have an audio adapter.
Sound cards.
I'm the only person in here in the audience team who doesn't have a pile of sound cards sitting on their desk. I don't know why. But they don't think of sound cards. They don't think of sound cards. They don't think of those things. What they think of are pieces of plastic, speakers.
Mm-hmm.
They think of microphones. They don't think of the, then underscore 8086 underscore dev underscore whatever, which are the plug and play guts. The old audio infrastructure actually, that paradigm was implicit in the way the audio infrastructure worked. We've changed that mechanism for Vista. We've changed it to reference something that's more closely appropriate to what users think about, and these are things we call endpoints. So we've got these MMDev API is an API that allows you to enumerate all of these endpoints.
So, I mean, in users in this case, you're talking about developers.
Developers, yes, of course. Yes. Well, but users as well, because
So
our
they-
control
who are
panel.
users?
What?
Okay.
But users as well, because when users interact with the control panel, the multimedia control panel, what we show them as the speakers and microphones on the system, those are in fact enumerating just the endpoints.
And we could put another box up there that says MMSys CPL, which
Oh, that's true.
also talks to all of these lower
That's
level
true.
components.
And that's the control panel.
And that's the sound and audio control panel. Forget
Yeah.
the exact name of it, but
Yes, I don't remember the name.
that's
of
where
it.
you control your audio adapters, your system sounds, and those sorts of things. And that's also been completely rewritten in Vista.
One of the
So,
things that we've
cool.
done, I mean, we've completely thrown out all of the old infrastructure. We've built a new one. It looks so much better now than the old one did. The old one was based in Windows 95. It was 10 years old, and it was pretty creaky. The new one's actually it's a lot more clean. It's a lot more usable. We've put a lot of effort into trying to make sure that we cover the core scenarios that the users deal with. So anyway, going through the APIs, back through the APIs. The other API, the second family of APIs we've added is device topology. And device topology is an API that is intended to allow an application to interact with the internals of the audio card. The idea is that there's this whole bunch of control panels out there that exist today. Right now, they use the mixer APIs, the existing mixer APIs, to try to intuit what's going on in the audio adapter. But because of the way the audio infrastructure in XP and before worked, they had to intuit. They couldn't actually know what was physically on the adapter because the system would say things like, "Oh, this audio solution doesn't have a volume control. I'll add one for them just because they have to have a volume control, right?" Well, that meant that there's a lot of hacks that go into place where people they would match the name of a control to see what the control did. And it was really a mess. It was really, really, really hard to program to this code. So one of the things we did for Vista, for control panel authors and for people who really need to manipulate the actual hardware of the device itself, we had a new API called Device Topology, which lets you explore and control the controls that are actually physically on the audio adapter. So if your hardware supports a bass control or a automatic gain control or also bass boost, bass tone, treble, whatever, all those controls are exposed through this device topology. And again, MMSys.cpl uses device topology to access and to surface those controls to users so that users can actually interact with them and use them. The core of the API set is an API we call Wasabi. That's the Windows Audio Session API. And
Great name.
the idea behind it is that this is the meat. This is the thing that handles rendering audio for all the applications that want to actually deal with audio. All of these the MMDev API is a standard COM interface. Wasapi and device topology are activated off of endpoints. So whenever you have an instance of a Wasapi object or a device topology, they're always associated with an endpoint. That allows us a significant amount of freedom beyond what you could do as a developer. The paradigm is really very natural to use as a developer. It's really, really simple and straightforward. And I'll be honest and say it's really nice to be able to just you enumerate, you find the endpoint that you want to talk to, and you say, okay, give me an audio client, and you're done. You now can start talking to the APIs that involve rendering audio. It's very, very fast access. Wasapi has 4 major families of, within Wasapi, the first API you talk to is iAudio Client, which is the main gateway interface. And within the iAudio Client, you actually have access to a series of other APIs. There's the iAudio Render Sync?
Render client.
Render Client. There's the iSimple Audio Volume. There is there's a couple of other ones. These are the ones that are the big ones. And the idea behind this is that you get an audio client, you get a render client, you say, for rendering, get me a buffer, and it hands you back a buffer. You fill that buffer up with your audio data, and you say release, and that starts the data being played out through the system. The simple audio volume allows you to change the volume of the audio session that's associated with that stream. Allows you to, it's a really, really simple, straightforward API. The render client has to start, stop, get buffer, and release. I think that's it. There's another iAudio capture client as well for capturing, for the inverse direction for capturing it. Same kind of an interface. You call get buffer, and you get a buffer, and you get the buffer, you read the data out, and when you're done with copying the data out of the buffer, you call release, it gets it back to the system. You call get buffer again, you'll get the next buffer from the system, etc. So it's really easy and straightforward to pull data in and out of the system. Do we want to go now?
I guess we can talk about the audio engine a little bit. I mean,
Okay.
we're not going to go into a lot of detail on that, but talk about a little bit of the guts underneath this, and then maybe talk about some interesting opportunities for ISVs and IHVs in audio in Vista. So sitting underneath Wasapi is the audio engine, and this is actually a service, a Windows service. And every iAudio client will build a stream in the audio engine, and then what happens is all these streams will be mixed, and then the audio data will be put on what we call a KS endpoint, as kernel streaming endpoint. And this is really where user mode and kernel mode meet up in the Vista audio stack. In XP, you hit kernel mode somewhere up here, because you had SysAudio and KMixer doing all of the interfacing and mixing. But now what happens is that this is all user mode all the way down to here, and then below that, so we'll just draw a line here. So this is user mode, and below here is kernel mode. And we have a single place that audio drivers plug in now. It's called port class. And this is essentially the same port class that we had in XP and before. And so this is a .sys file, a kernel mode driver. Port class works on what we call a mini port model. So in XP, there were two main kinds of mini ports that plugged in. One was Wave Cyclic, and the other was Wave PCI. And in Vista, we've also introduced something called Wave RT, which I'll spend just a short amount of time talking about right now. What a Wave RT driver does, and this is part of something we call UAA, or the Universal Audio Architecture, is it allows the direct mapping of DMA buffer memory, which is what's on the audio hardware, to user mode. And so what happens is that if you have a Wave RT mini port driver, there is a region of memory that it uses to capture the audio data. So this is DMA memory. And, excuse me, let me try to make that up. And this is the actual memory that the audio adapter uses to send to its digital to analog converter and then to your speakers or headphones. And through a technique that we've implemented in UAA drivers in Vista, we will map this memory up into user mode. And so when the audio data finishes getting mixed amongst all the streams, we will collect that mix buffer into the KS endpoint and then copy it into this memory that's been mapped onto user mode. As soon as we copy that memory, it's on the audio hardware, it's on the DAC, and streaming out the hardware. So this is one of the big ways in which we have a big performance advantage on Vista, is because we don't have to run a thread or do any copying when we're transferring the data from user mode into kernel mode. And so that's one of the big ways we got a really big performance win, even though we moved a bunch of the stack up into user mode. And so that really gives us a lot of flexibility. Two more points about the audio engine, and then we'll talk about some opportunities. One is that in XP, IHVs, or independent hardware vendors, would build a lot of their value add down in kernel mode in their drivers. And this has two difficulties, which we talked about before. One is that you have an issue with programmer talent pool, and the other issue is if you make a mistake down here, you take down the machine, which we all call the blue screen of death. So what happens is we have these things called system effects. These are pluggable objects that can can be put into the Vista audio engine pipeline, and this will allow some kinds of digital signal processing, like microphone array processing and channel fold down and some other kinds of end user effects, and allow them to be programmed in user mode. The other advantage we have is that for those kinds of applications that don't want multiple streams mixed by our engine, and this is pro audio content creation apps like Cakewalk Sonar or DigiDesign's Pro Tools, they can run application in what we call SAPI exclusive mode, and we will put this buffer, this mapped DMA buffer memory, all the way up into application space. And so when they are writing their PCM data, they will get the advantage, they will get two advantages. One is very low latency, because they will get their audio data down onto the hardware as quickly as possible. And the second thing is we guarantee to not be in the way. We won't do any digital signal processing of any kind on that thing. And that's what we call exclusive mode. So there's a lot more opportunity for people to build high-end audio applications in ways that are much simpler than they were before, because they no longer have to write kernel mode drivers in order to get low latency audio access or certain kinds of digital signal processing on audio streams in the Windows operating system.
And that's a huge point. It's worth re-emphasizing. So it's
Right.
now easier to write highly powerful, useful applications for audio without having to write drivers
Correct.
in kernel mode.
Correct.
And so now let me ask you this. Obviously, we're in unmanaged world for programmers. They're still writing
Correct.
unmanaged code in this model.
Well, this one of the say, what's the politically correct way to say? One of the ways in which we enabled shipping of Vista was to pull back from the range of languages and APIs that we support. And so one thing about the WASAPI interfaces and MMDave API and device topology is they're most amenable to being used from C++. And managed code is something that we will address in the future.
One of the challenges associated with Managed Plus is that the Managed Plus, the scheduler under when you're running with managed code, is not totally deterministic. And so when you're dealing with inherently isochronous data like audio and video, where it's critical that you be able to run all the time, and you've got to get those audio samples out to the audio adapter on time or you're going to glitch. It's a challenge. It's a very serious challenge to get out of the way of the managed infrastructure, which can sometimes introduce delays. And so there's a challenge associated with making sure that an application that is isochronous in nature can run in the managed environment. And as Elliot said, for simplification, in order to basically make Vista available on time, that was not a challenge that we chose to address at this time. We'll take care of that sometime in the future at some point. One of the really cool things, by the way, about exclusive mode and shared mode is that from an API interface, the difference between exclusive mode and shared mode, it's a flag. It's a state that you set when you initialize. The APIs that the application deals with are identical, whether they're talking to the full audio engine or they're talking directly to the hardware for the RAVE-RT. It's just, you just say, I'm initializing in exclusive mode or I'm initializing in its shared mode, but you still use the same get a buffer, release. But in the case of exclusive mode, when you call get buffer, when you're dealing with a WAVE-RT driver, the buffer you're going to get is the DMA buffer that you're dealing with. And the release, I don't think actually, does it do anything at that point when you're dealing with WAVE-RT?
Not in WAVE-RT.
Yeah,
Release
in WAVE-RT
buffer is a
exclusive
no
mode.
op.
Yeah. So it's really nice that we've a single programming model for both talking directly to the hardware as close to the metal as you possibly can, or dealing with, coexisting in a rich infrastructure with all the other applications. One of the other things that we did not mention, by the way, that's a significant change from Windows XP in the old model, has to do with the actual format that's being rendered. One of the behavior characteristics of the XP model was that it tried to be as flexible and friendly to applications as possible. And what that meant was that when an application started rendering, it would lock the audio pipeline into the format of that application. And what that meant is that it did the least digital signal processing possible for an application, regardless of what the application was doing. This is actually really great and flexible because it means that when you're playing system sounds, the system sounds which are rendered in 22 kilohertz stereo come out as 22 kilohertz stereo. We don't mess with the signaling. When you're playing your CD, it's coming out in 48 kilohertz or 44 kilohertz or whatever the rendering speed of the CD is. And it's really pretty good because you don't get any mixing, any problems, any signal processing. The problem happens when you start playing your CD at the same time that a system sound is playing. So now you have your nice 44 kilohertz CD audio, and it starts playing, but the engine was locked at 22 kilohertz because that system sound was playing. The system is now going to take your 44 kilohertz nice CD audio and downsample it to 22 kilohertz. And now all of a sudden, through no fault of your own, your CD sounds like junk just because the system happened to go ding at an inopportune time. And there was no way for a user to control this. There was no way for a user to actually manage that experience. And so one of the things that we've done is we said, okay, you know what? This is a horrible experience for users. They want to be able to hear their CDs at high quality. They want to be able to hear their audio at really high quality. We want to enable scenarios where we stream very high quality audio through these audio solutions that users have paid a lot of money for. We don't want to have a situation where the system will actually degrade that accidentally. So one of the things that we've done is that the mix buffer that we talk about here, this mix buffer is actually controlled by the user. The MMSys control panel actually says, what's the format of that mix buffer? It's going to be 44 kilohertz, 22 kilohertz, 128 hertz, I don't, 2200, whatever, doesn't matter. The user says this is what the mix format is. That's the format that we're going to render out of the pipeline. And we push the problem of figuring out how to do sample rate conversion. We've pushed that up to the application. We've said, okay, this is the rate at which the audio engine runs. The audio engine runs at 44.1 kilohertz or 48 kilohertz or 96 kilohertz, whatever it is that the audio engine runs at. It runs at that format. You need to give us samples at that format speed, at that frequency, at that sample rate. And we won't do sample rate conversion. It's your samples. You do them, and we'll render it through for you. But the nice thing about that is that it means that we'll never get into a situation where an application can accidentally can upset and mess up the experience of another application. For compatibility reasons, the Wave APIs will still do sample rate conversion. We will still do format conversion for the Wave APIs because because we're not going to break compatibility. We're not going to push that problem up to old legacy applications. But for new APIs, for applications that are using the new architecture, we can guarantee, and we do guarantee, that their audio experience, that what they render at the application when you talk to WhatsAppy, that modulo a couple of possible issues or possible changes is what goes out the speakers.
So that's a good way to describe what the dividing line is right here. If you're the kind of application that knows how to do sample rate conversion and you care about the quality enough to have written your own sample rate conversion, you can talk directly right here to WhatsAppy. If, however, you're an application where sound is not the primary goal of the application and they may not have the expertise or want to build sample rate conversions or format converters into their application, they can still talk to all of these APIs at this level, which will do that sample rate conversion for them. So there's a lot of flexibility there. I mean, there was always this level of API in the system before, but we never really had this level of API that was available to audio applications for the Windows ecosystem.
So, really nice.
I want to also talk just a smidge about volume, because volume is very close to my heart.
Near and dear to
Near and dear to my heart. I have been dealing with volume for 3 years now, I think it is. Yeah, 3 years plus. So, the way the volume control infrastructure works, one of the things that happens on every audio stream as it's flowing in, before it gets to the mix buffer, let me take a step back. Every audio stream in Vista is associated with a thing we call a session. And I hate the word session in general because it's so horribly overused. Everything's a session. Terminal server sessions, networking sessions, everything's sessions. We call them sessions anyway. Every stream is associated with a session, and now sessions can hold more than one stream. By default, unless you do things to change this, the boundary of a session is a process. So every stream in a process is associated with the session for that process. And we give you other ways of dicing and slicing those, but in general, in default, if you don't take any special actions, the session is a process, and all the streams for that process are associated with the same session. Every session has a volume control. So when you talk to the simple audio volume, you're actually talking to the volume control on the session itself. The way we make that work is we actually tap on the stream, as the stream is running through the engine, we actually insert a volume control into each stream. Into the data flow of the audio through the engine. And when you manipulate the simple audio volume, what we're going to do is we're actually going to manipulate the volume control on each of those streams.
What is volume?
Oh, that's a good question. If you look at an audio stream, an audio sample, it's got some waveform.
Sure.
And each of the sample, a waveform is actually an audio stream, a digital audio stream is actually composed of a series of samples that are taken across this waveform over time.
So when you hear us talk about samples per second, that's how many samples we sliced up
Yeah.
that part of the waveform.
How many vertical lines there are in the thing. The
So
more
for
vertical
example,
lines, oh, sorry.
Go ahead, Larry.
The more vertical lines, the better your fidelity. That's the sort of simple case. Is that the more lines, because the closer you're going to get to reproducing the curve when you sit down and draw the lines back without the curve. So, sorry.
So a CD is broken up into 44,100 samples per second. That means we have 44,100 chunks per sample. And this is all encoded in what we call PCM, or pulse code modulation. And basically every one of those samples is a single 16-bit integer value. And simplistically speaking, the larger the number, the higher the volume.
Exactly.
And so what we do is, in the volume APO, Larry,
If I'm going to do a 50% volume, I just take those samples and I cut them in half. And what you end up getting is a curve that looks just like the original curve, only it's half the size.
but that's slightly oversimplistic. We apply some
yes.
DSP and do these things we call ramping, but conceptually that's exactly what's going on.
It turns out that you can't apply, if you're applying this immediately to a curve, you can't immediately apply the volume change to, say, the next sample. You need to ramp the change over a series of several milliseconds, because if you do it immediately, there's a transient impulse that occurs and you hear a pop noise.
Yeah, it sounds like a glitch.
It sounds like a glitch. It's actually kind of wild. Before we put before we put that in, you'd move the slider up and down, and it would go.
Okay.
It really did say it was very, very, very obvious what we were doing wrong.
So now, are these still 16-bit ints, or are they 32-bit floats? As you talked
Well,
about
that's an interesting question. When the samples are flowing through the pipeline, they are float 32, and so it's an interesting question, because the data that's coming in might be a PCM file, which is integer 16, and the audio hardware might be integer 16 on the very other end when we do the output. So we will convert to and from float 32 to integer 16 as appropriate. So typically what that means is we'll convert to float 32 on the entry to the audio engine, each stream in the pipeline, and then right before we put it on the hardware, it will be converted back to integer 16. But all of the digital signal processing is done in float 32. And of course, if you happen to have a float 32 content to begin with, all the better, because then we don't do a format conversion from int16 to float 32.
One of the things that we've done, for instance, when you're rendering through Media Foundation, this did happen, right? Elliot?
Sorry, what's the question?
This did happen, right?
What did happen?
The MF to 32 to float.
Yeah.
Okay,
Yeah.
sorry.
No problem.
There was a long series of discussions in house about whether MF would make this change, but they did. So when you render MF, so MF is decoding a WMA file, for instance. WMA files are encoded with 16-bit integers as they're when you decode, you get 16-bit integers. MF will do that floating point to the into float conversion for us very early on in the decode stage, so that again from the MF all the way through, and that way MF can apply if it has to do digital signal processing internally on MF side, it does that all with floating point, and thus we get the benefits of the full 32-bit floating point number or calculations with the rounding error issues and things like that, all the way through the engine. So we don't incur, under many scenarios, we don't actually incur floating point conversions. Also, there are some fairly significant number of adapters that exist today, of audio solutions today, that support rendering floating point. And if the audio solution supports rendering to floating point, we won't do conversions on the bottom end, because we presume that the audio adapter, the audio solution, has a better ability to do float conversion in their DAC than we do. At a minimum, there's going to be sample loss when you go from 32-bit float to 16-bit, so we want to push that off. If the DAC can do the 32-bit, if you can do a 32-bit float DAC, then we'll be more than happy to let it do the work, because it'll do a better job than we will.
Now, can you briefly explain why it is better in the 32 or 16 world? I mean, you have a larger number, so you have a larger range of...
Yeah, exactly. The easiest way to explain it is, let's say you have a bunch of high volume content, modern rock music in PCM waveform type of format, and you happen to mix two of these together. So you've got two 16-bit integers that are close to the max int value, and you mix them together. When you mix them together, you don't double them, but you will get some sort of amplitude gain when you mix those two signals together. And if you have two 16-bit integers that are close to their maximum and you apply the mixing algorithm on that, you might overflow the max int. And that's what we call clipping. And I think most people are familiar with, in home audio systems, if you drive your system into clipping, it will sound very bad. Now, if you contrast that to an integer, a float 32 sample, now we value those between 0.0 and 1.0, or we'll take those and we'll put them into that range. And so you might have two pieces of hot modern content that are close to 0.90, and you mix those together, is you will not actually overflow that integer because there's a lot of room above 1.0 in a float 32, and there's a lot of digits of precision for us to do the mathematics on that. So it allows us to do these kinds of digital signal processing without incurring integer overflow. And so that's really, it's very, very simple math why float 32 is better than N16. And it's well recognized in the audio industry that 32 and 64-bit float is the way to process audio data.
And some of the digital signal processing algorithms we have are based on things like fast Fourier transforms and various different forms of digital signal. Well, all of those algorithms were derived with the assumption that they were dealing with floating point data, and so they translate very naturally. You could take advantage of the floating point coprocessor to do a lot of the math that's associated with it. Otherwise, you're going to lose, and you can lose quite a bit of resolution when you start, if you're trying to apply those techniques that were designed for floating point mathematics. When you try to apply those techniques to integer content, the losses can really, really add up really quickly.
So now, why wasn't it originally a floating point 16? I mean, why? Is that? May not make sense.
Oh, actually, it's a great question.
Yeah, it's a great question. This is historical, and this audio system has its roots in Windows 3.1 and then Windows 95, which I believe is when KMixer was introduced. And it was 98. It's a lot more difficult back then. It was a lot more difficult back then to do floating point processing. So
in fact, actually, it was until the 486. No, until the Pentium came out, you couldn't guarantee that the processor actually supported a floating point numbers. You might have to do them with floating point emulation. So up until the Pentium class machines came out, even the 486, well, the 486SX was a machine without a floating point coprocessor. You didn't have the hardware wasn't there, and frankly, the hardware was slow. It was. And if it was hard, if you had to do emulation in software, oh my goodness, it was horrible.
So 8 and 10 years later, after the birth of that origin of the audio pipeline, it was really time to go to Float 32. Yeah. And Vista was the perfect opportunity for us to make that transition.
Fantastic. And that is a big transition. I mean, it's fantastic. Now, on a 64-bit system, right, are you going to take advantage of...
So that's an interesting question. On a 64-bit system, it's still a Float 32 pipeline, but we've built the architecture of the Vista audio system so that the internal processing of the samples is transparent to the application. So if we ever wanted to convert to a Float 64 kind of pipeline, that would be invisible to the applications. Everybody who's ever built what we call an audio processing object will have to change to Float 64, but everybody else, which is everybody who's talking to a SAPI or the renderers above it, will find that kind of change to be mostly invisible and transparent.
One of the challenges of going to a Float 64 is that you're now pumping twice as much data across these boundaries, and so with 32-bit content, we know that the CPU costs associated with actually just physically moving the bits around through the system is totally manageable and very reasonable. If we were to double the size of the samples, it's not entirely clear that we would be able to see. There would be a CPU cost associated with that, and it's not clear how that ends up playing out. So for now, we're on the current class of hardware for the current systems. We're not going to do that, but in the future, you never know.
Fantastic. Well, with that, thank you very much for your time.
Yeah, thank you for talking to us.
It's great.
We hope a lot of people use audio and write those audio applications on Vista.
Yes.
Please do. Thank you, guys.
Thank you.